Well, hi everybody. Wanted to take a few minutes to go through the homework that we just finished that I graded, um, and share with you some of the things I found as I went through this myself. So let's just get to it, shall we? So what we found was that, or the assignment was that we had a home air conditioning unit. This was a unit I used as an example, and I found the specs online. It uses R410A and has a capacity of 10,150 BTUs per hour, and it had a EER of, I forgot what it was, but it came to a COP of 3.16. We didn't need that to do this assignment, but I'm going to close with a little discussion of that. I told you to assume a condenser temperature of 120 degrees Fahrenheit and an evaporator temperature of 50. I gave some thought to that, and we talked about that in the review process, that we don't know exactly what it'd be, but it's going to be different than the outside temperature and the inside temperature. Just a real quick comment about the refrigerant they use. This is our 410A. It is unusual in that it is not a pure substance. It's a mixture. And that's important because the saturation characteristic isn't quite the same as all the other refrigerants we've looked at, or that you've probably looked at. It's called the refrigeration folks say it has a slide, so that for constant temperature and saturation, the pressure is a little bit different. I didn't take that into account in this analysis, and I didn't expect you to, though if you use the tables, you probably did. It's just something to be aware of. It's not really pertinent to our discussion right now, but these newer refrigerants are a little more complicated in their behavior. Okay, so the part one of the homework, just to review what the homework assignment was, recreate the analysis I did in the video. Basically, just look up the properties and make sure you know how to do that. You can use the tables that I posted in the Canvas site as a PDF, or there's other resources available as well. When you're done with that, then use those values to find what the system was doing. So the other piece of information we had was the cooling capacity, 10,150 BTUs per hour. From there, you could find the mass flow rate. Then you could find the compressor work. You could find the COP and the EER, the energy effectiveness ratio. Then part three is just repeat the analysis for 3 different condenser temperatures. So we'll actually have 4 data points to look at how the system behaves in different outside conditions, because it's the outside conditions that set the condenser temp. And then I asked you to just tell me what you found. Just make some observations about the effective condenser temperature. So we've seen this before. This is the TS diagram of the vapor compression cycle. I've taken this right from the previous video. I added the state numbers here, so just to walk you through it again, this is the inlet of the compressor, state 1. It's saturated vapor. It's sitting on the saturation dome. It's at low pressure and low temperature. You assume an isentropic compression, go to a high temperature, high pressure. You're out here now in the superheated region. This is state 2. This is the outlet of the compressor. And it enters the condenser where it's rejecting heat. So it goes through the de-superheating, they call this region, back to a saturated vapor, through the condenser. This whole line here goes through the condenser. And we assume what comes out is a saturated liquid. It might be subcooled a little bit, but it turns out that doesn't change H very much. And then it expands through an expansion valve to a mixture here within the saturation region at the low temperature, low pressure. And as it evaporates in the evaporator from 4 to 1, it completes the cycle and absorbs a great deal of heat. And that's the refrigeration effect. So here's the refrigeration effect here from 4 to 1. There's the compression. And then this is the heat rejected at the condenser from 2 to 3. Since the line from 3 to 4 is isenthalpic, the enthalpy doesn't change. There's really no energy change here in this part of the process here. Okay, so most everybody did this right. You went into the tables, you found it. There's other ways of doing it. I will say this, not everyone got the same superheat in here. There's that double interpolation is a little tricky. I went and did it twice just to make sure I had it right. Then I used other sources, and it all comes out. It's about 150 degrees at the outlet of the compressor under these conditions. About 433, 434 psia for the higher pressure, These H's were pretty consistent. Some variations in the entropies, 2459 or 0.259. I saw both of those. I've used both of those depending on whether you use the tables that I gave you or the IRC property calculator. And then the quality at state 4 is about 0.33. Okay, now I mentioned there's other property calculators available. There is the Industrial Refrigeration Center, University of Wisconsin. I gave you that link last time. You can Google it. It's pretty easy to spot. There's also an Excel plugin from the University of Alabama. It took me a while to get it to work on my computer, but it's not too bad. You have to kind of poke around, and it's fairly self-explanatory, but it's essentially lookup tables for property values. I get very similar results, but it's important to know that I don't get identical results if I go to different sources for the thermodynamic properties. It's also important to realize that enthalpy and entropy are not absolute properties, and by that I mean they're not referenced to an absolute zero. They're referenced to an assumed, zero state, and not all sources of thermodynamic properties use the same reference state for those properties. And indeed, the Excel plugin I used gave me enthalpies that were about 60 BTUs per pound mass bigger consistently. It just used a different reference state. So since almost all the analysis are delta H's, H4 minus H1 or H2 minus H1, then that doesn't matter. But you can't mix and match. You can't go to one source for some properties and then say, well, I'll go over and use another source for the other, because they may be at different reference states, and that'll totally screw up your analysis. Okay, now part 2 is, given that you filled out the table like I showed you in the previous video, go ahead and apply the first law of thermodynamics to each component. So the QL dot, which is the heat being absorbed by the evaporator, which is the refrigeration or cooling capacity of our system. That's the key right there. It's equal to M dot times H1 minus H4. The condenser equation is pretty straightforward. The compressor equation is straightforward. And the COP is a ratio between what we want, which is the refrigeration effect, QL, divided by what we have to pay, which is the compressor. Right? So the M dots canceled. The COP is just that ratio of the change of enthalpies. Several of you got this wrong. Either didn't figure out that you needed to do this, or we're getting the subscripts wrong. So please be careful. It's not rocket science here. So if you have any difficulty seeing where these come from, ping me on this, and I want to clear that up. There's another point I wanted to make. Oh, so these equations are very simple equations. They come from the first law analysis. But if you remember from thermodynamics, the true energy balance of a system has other components, right? They've got potential energy, change in height, right, against the gravitational field. They've got kinetic energy, the V squared over 2. We are ignoring those. We're assuming that doesn't really have any impact on this analysis. Usually pretty good, but I just want to keep in mind, we want to remember these equations have a formal derivation, that we made a lot of assumptions to get there, because sometimes when you're doing research or you're really kind of pushing the envelope of an analysis, those assumptions need to be revisited. Okay, so even if some of you got those equations, you didn't realize that we had enough information to get the mass flow rate, and what we needed was realizing that the cooling capacity of 10,150 BTUs per hour is QL dot. And from that, you have all the H's from the other analysis. We can say that the mass flow rate under those conditions is right under 170 pounds mass per hour. Now remember, there's not 170 pounds mass of refrigerant in that system. The whole system probably weighs about 60 pounds. But an hour is an awful long time, so it's probably, you divide by 3,600, it's a lot less than a pound per second. There's probably less than a pound of a refrigerant in a small air conditioner like this. The COP you calculate out here is around 5, but again, depending on where your properties come from and how many significant digits you carried around, I got 5.1, I got 5.2, so it's very, very sensitive to enthalpy numbers. EER is just a quick change over from 5 to 17.1. Just all of you saw that conversion factor. It's BTUs per watt. And then the heat rejected in the condenser is 12,180. And it's just, if you do the math on this, it's the compressor work plus the refrigeration effect has to equal the heat rejected. That's the whole system has to be consistent with the first law as well. Okay, so that was part 2. Part 3 is just carry out the analysis again for 3 more condenser temperatures. And keep in mind that changes everything, right? Or just about everything, because if the condenser temperature changes, then its pressure changes. Higher temperatures means higher pressures. That means the compressor's got to work harder. So you're going to have to change. You're going to have to, you expect a different compressor work. And I ask you to assume the mass flow is constant. It's not going to be. The mass flow rate, the volumetric efficiency of the compressor changes with its pressure ratio. It gets a little bit beyond what we want to do, and it gets really hard. So just assume it's constant, and we'll get useful information. It just won't be entirely accurate. But just keep in mind that as you change the condenser temperature, the only line in our table, the only state that isn't affected is state 1, which is the inlet of the compressor. So this little table summarizes what I found when I went through this analysis, and I put our baseline in here at 120 degrees Fahrenheit. And we see the COP has changes wildly. So does the actual amount of refrigeration that you can take, the cooling effect, and of course the EER just scales with the COP. And I graphed it up here to get an idea of what it looks like as well. So as you come down here, you can see it's starting to level off a little bit. Under normal conditions, you really wouldn't expect the condenser to get much higher than about 140 anyway. Again, some of the students struggled with this. I think just because it was sloppy table work. At 80 and 100 degrees Fahrenheit, some didn't get the superheat right. In fact, some showed no superheat at all for the exit of the compressor. Exit of a compressor is always going to be a superheated vapor. There's no way it can't be. Okay, so that's an important thing to keep in mind. Okay, so just a couple more points before I wrap this up. And I want to go back to something I talked about at the beginning of this, this rated unit has an EER of 10.8, which is pretty low. For a whole house air conditioning, the federal regulations now have a minimum of 13, but this is a window air conditioner, and those regulations aren't as intense. It's still a COP of 3.16, but our baseline, which was intended to mimic the test conditions that they would give the specs for, showed a COP of 5. So the question is, what's wrong? Did I get the test conditions wrong, or is there something else there? So here's just a quick run through of what I thought of off the top of my head. So in the baseline case, that analysis in that table, if you look at the difference between H2 and H1, multiply times m dot, we get a compressor work of about 2030 BTUs per hour, which is 1/5 of the cooling capacity, exactly what we'd expect. But that assumes an ideal compressor, isentropic, 100% efficient. Let's assume it's not, and we know it's not. And I just pulled a number out of the air, 85%. It's brand new. Let's just go with that. It's probably not a lot higher than that. It's probably not a lot lower than that. But it could be 75. It could be 90. Probably not. It's probably in the 80s. So you divide by 0.85, and now our compressor work is 2388 BTUs per hour. That's about 0.7 of a kilowatt, which is about 0.94 horsepower. That's kind of a nice round number, I think. Considering I just took a guess at the efficiency, they don't tend to size motors for anything other than round numbers. So the fact that it got close to a horsepower makes me think that we might be on the right track. The efficiency might be a little lower. Maybe I didn't get the test conditions quite right, but I'm in the ballpark. It's probably a 1 horsepower motor on the compressor. The unit, the air conditioning unit, also has blowers. Now, the thermodynamic analysis doesn't talk about moving the air across the evaporator or moving the air across the condenser, but you certainly have to pay for it. And the EER, the rating of the unit, takes that into account. So again, I just took a guess and said maybe it's a 1/4 horsepower motor. It's a small motor that'll fit in there. It's got a lot smaller than a compressor. It doesn't have nearly as much work to do. And let's say it's the same motor, probably has a impeller on each shaft, one blowing the air across the condenser, which is outside, and one blowing across the evaporator, which is inside. So that 1/4 horsepower comes real close to 600 BTUs per hour. Add that up. So now the energy the cost we're paying for the refrigeration effect is a lot closer to 3,000 BTUs as opposed to 2,000 BTUs. So now my COP is at 3.4, which is a lot closer to the rate of 3.16 that we had before. You could go back and refine that and say, okay, well, maybe that means the efficiency should be this or something like that. But to me, since I really don't know what the test conditions were that the ratings were set to, and there's probably some ISO standard somewhere we could look that up. I think that's good enough for today. I think that was a good back of the envelope thinking, I think we did a pretty good job there. So just a few closing comments. In working the problem, I found that COP particularly was really sensitive to H, to the enthalpy values. In fact, I actually did a little sensitivity analysis. I took the equation for COP and took its partial derivative with respect to H1, and then looked at how a delta in H1 affects a change in the COP. And in the range where we're looking at, it was about 0.5. In other words, if you change those enthalpy numbers, which were like 120, 60 to 120, change it by just 1 point, so 120 to 121, it changed the COP by a factor of by 0.5. So that change in that H1 from 120 to 121 would change the COP from 5 to 5.5. So that's what I mean by really sensitive. Small changes in the enthalpies made big changes in the COP. And that's why it's important to be meticulous. The tables that we had in the PDF had 4 significant digits. The IRC calculator, the Industrial Refrigeration Center, didn't. It only had 1, or it had 3 significant digits, sometimes fewer than that. So it's not going to be as accurate. And I think the bottom line is to realize these are analyses that you really can't take to the bank. We're working at real world systems. We're making a lot of idealized assumptions, but they're good comparisons. What was valuable out of this analysis was looking at how the thermodynamics change with changing in ambient conditions with the condenser temperature. That's I think significant and important to keep in mind. So that's it. That's all the analysis there. Again, any questions, send me an email, and have a great day.